Yeah, thank you for having me and for the introduction. Yeah, the slides already say it. What I'm going to talk about, I will just expand on this a little bit. Just before I do that, let me just say 2 words about myself. So the colors look nicer on my screen. But yeah, this is where I'm coming from. I was born in Germany, in Mainz. I was a pure mathematician for the most time of my life. I did a PhD on these beauties here. So algebraic geometry, equations, stuff like that, geometry. And then I switched to IT at a certain point and worked into statistics and data analysis for a while at the University of Koblenz. I was a while freelance consultant, and I'm finally now arrived at a very exciting place, which is a Circonus monitoring vendor. And Circonus is a monitoring vendor which is able to scale to pretty large installations. We have clients of us which are pushing millions of metrics in, 4 or 5 million metrics on a minute basis. So we have a massive amount of data. This is a big contrast when you come from a university setting. There you have a lot of brains, but you have no data at all. And now we're sitting like on this ton of exciting operations data, how systems behave. And Circonus is available as a public SaaS and a private SaaS, so you can install it in your own data center. And I invite you all to just have a look at it and try it out. We have free accounts, so if you want to try it, you can just sign up for it and have a look for yourselves. And the last bullet here is what I'm mainly concerned with. It's about our analytics functionality. So we do forecasting, anomaly detection, and we have a built-in histogram data type, which is quite nice. So this talk is structured in 3 different parts. The first part is called The Future of Monitoring, a really bold title. It's actually alluding to a blog series we currently have on Circonus.com by our founder, Theo Schlossnagel, who went around the hallway tracks of a lot of conferences and interviewing people how they're seeing the future of monitoring. And we currently have a blog post by John Elsbaugh there, and a few more are in the pipeline. So this is a bit inspired by that. The second half is going to be a bit more about software design. So what design patterns can you use to analyze streams of data? And the third part is about architecture of our analytics engine we are currently building. Right, so let's jump into it. The future of monitoring. So I put on here a cloud monitoring challenge that it's actually many of the people who approach us, they say our infrastructure looks like this. So we have 100 containers in the fleet servicing or implementing a certain service. We have 200 metrics we want to collect per container. So these are infrastructure metrics, operating system metrics, and application level metrics, just everything you want to measure inside. And then you have 50 code pushes a day. And for each code push, all the containers are recreated. So you shut them completely down, and then you recreate them. So you will at first create 20,000 metrics for the fleet, and then you bring them down, and they come back up. And you will have, again, new metrics you have to create, or you use existing metrics. But that's a lot different from what we have seen earlier in more static environments. So here's, for example, a classical visualization of CPU utilization for a database cluster, which has 6 nodes. And you can see what's going on. So they had a batch job running, and it's going up, and somehow it finishes around 12 a.m., and then everything is back to normal, so you can make sense of this diagram. Now, imagine what happens if you are drawing the CPU utilization of this configuration of 100 containers on the screen. So I give you a brief look at that, how this might look like. So this is actually just 10 metrics, which are a little bit fleeky, but you get the idea. It just will not be able to make a lot of sense out of this massive amount of data which is arriving. And the characteristics of this data are also changing. You no longer have line plots which extend over a long amount of time. You will have like little chunks, some nodes coming up, some nodes getting down. And so the classical visualizations are really pushed to the limits. And also the architecture behind data storage for monitoring, which is also has to be adapted for these scenarios. Here's a quote from Herbert A. Simon, which is taken from the interview with John Elsbaugh. And the quote says, information is not a scarce resource, attention is. So Herbert Simon is a psychologist, founded a theory of cognitive psychology around attention. And so this is really the challenge for us to be resourceful with the attention of people. So we do not want them to look at a big complex graph with a lot of things going on there, and you have to figure out yourself what's really the information in there. But I think the challenge for the monitoring industry becomes more and more designing user interfaces and analytics methods which really help you as a user to find the relevant information quickly and help to make sense of this whole gigantic mountain of information we are sitting on. And data science has to play a role in that, but also UI has to play a role in that I have to be able to drill down in certain things. So here are two examples like how we think that the monitoring field might evolve or what kind of methods we will be seeing to do that. So one is extensive use of histograms. So this is basically a picture of the same data you were seeing 2 slides before. It's 20 database nodes which I'm plotting the CPU utilization. And each node for each time frame, the CPU utilization is put in a histogram which we view by color coding. So you're no longer seeing a line plot which extends through and has this continuity to it, but you're for each time seeing the distribution of your CPU utilizations across the cluster. One nice thing about this is, not only that it looks pretty, the other thing is it's transparent to the amount of nodes you have in a particular bucket. So there can be 20 nodes in this histogram and 3 nodes in this histogram, and it doesn't really matter. The view to your data and the underlying data structures are just the same. They're just more, just more data in it at one time than there is at the other time. And what I plotted on here is the 90th percentile of these histograms. So 90% of your CPU utilization is below this bar. And this is a sensible like aggregate statistics, which you might want to compute across this database cluster to see if 90% of my nodes are having high CPU utilizations, I might want to do about that. If 95% of my nodes have 95% CPU utilization, I might want to have an alert. So this kind of online processing of histograms is one theme that we see in the future, and we are working on making things like quantile-based alerting happen. Here's another view to your data. Here, it's actually a mock-up, so it's one of like internal stuff we're debating. So if you open Circonus and you have 4 million metrics, then you will see 4 million rows in an HTML table, which is paginated, but you can click through. And you will see values, and you will see plots, and you do not really know what values you should be looking at the moment. And this is, I think, the key application domain for anomaly detection, which we see a lot of talk around in monitoring industry. So what it can do is basically tell you, for a given metric, does it look normal compared to historic values? And given on that, you could compute a health status of the metric. And then you get this little bubble saying you, okay, this looks all right, it's green, or this looks out of the ordinary, it shouldn't look that way. And of course, this is just right now a little visual clue. Okay, that's nice, but you can do interesting things with this now. You can sort the whole amounts of metrics by the health status to see what metrics are behaving out of the ordinary. You could then think of active learning lab methods where you could click and say, okay, you detected this is actually an outlier or an anomaly. I don't think it's an anomaly. I will give feedback from the administration or the operations side, say this is not something I'm interested in. Please retrain your methods. So these are analytics methods which I think would be useful in the future. And there's another thing you can do with anomaly detection, which is postmortems. So if you're having an outage, and you have solved that, or you have had a problem a few days back, performance problems maybe, you can go back and you will like to know what was the probable cause or a possible cause of that problem. You can go back and look at all the metrics which are behaving out of the ordinary and just sort by the anomaly scores you were observing in this given time frame. So that's another theme we might be seeing and which can create useful information. Great. So let's talk now about how we might be able to realize those methods and how to implement them. So there's a theme or a two division between two basic patterns we're seeing here, and one is the online analytics and one is the offline analytics. The offline analytics is something more familiar. This is when people refer to monitoring as a big data problem, they usually mean offline analytics, which means I have this huge database and this pile of data, and I want to make sense out of that, and I want to make, for example, postmortem analysis, or I want to maybe learn thresholds or something which is a little bit static and works on the big database. On the other hand, things like anomaly detection or percentile alerting or smart dashboard widgets or stuff like this, this is a stream processing problem. So you have to operate on the incoming data stream. Right. So we are aware that these are very different problem domains, and so we are right now building two components which have the beautiful names Beaker and Bunsen. And they fit into a whole zoo of Muppets that we call our internal infrastructure components. So this is a picture from our kitchen in Circonus office. The Beaker online alerting engine will sit right in front when the data comes in and transforms metrics. The basic pattern is that we have now metrics incoming the system, just usual metrics, which are directly forwarded to the alerting service, and you send alerts to a mildly happy user. I mean, he's happy because he gets alerted on it, but there might be a problem, so he might not be perfectly happy. And you now have, with Beaker, the idea is that you now transform the incoming metrics into new ephemeral metrics, which are just computed artifacts, but are actually treated in the rest of the system on equal foot with the incoming stream. So you could have a database cluster which sends histogram data into the system, you compute the quantiles on it, and then you can do everything you could do with the individual CPU measurements just with the quantiles which are already arrived. So you could alert on them, you could persist them if you like, you could just recompute them if you want to view them in a graph. Right. So this is a thing that very much lives at the incoming side of the data. The Bunsen offline analytics engine, this is very much something that sits on the database. Right. Design patterns. So I'm going to, from now on, only talk about the online analytics part of it. When we see online computation done at many parties, they often take a window-based approach to it. What you do is you start with your data stream. I have here a little bit of Python code, so here's your incoming stream. Then you have a method which transforms the stream to streams of windows. And then you apply a method to each window, and you are returning a value y. Right. So this y is actually different from this y, so I apologize for that, but you get the basic idea. You have some set of incoming data, some stream, you calculate windows from there, and then you apply methods to it. This is a very common theme. For example, all supervised machine learning methods operate on that. What they typically do is they take this window, then they apply some transformations, which they call features. Could be just mean values, might be Fourier transformations or stuff like that. And then they do a pattern matching algorithm, or like a support vector machine or something, trying to separate clusters or learn categories of these feature vectors. But this is very much like basically you're forcing it into an offline domain. You have a set of samples now, and you are doing classical machine learning on it. So Fourier transformation is a really a popular approach to that. For example, if you know Winamp or like this music visualizations things, they do precisely that. They take a quite large window, and then they take the Fourier transformation, and then you see this as a heat map visualized on the vertical axis. Right. And there's also anomaly detection implementations. For example, there's one by Etsy where Andy Clegg talked about this year actually quite a bit, which uses a similar approach. And there are also frameworks around that which allow you to work with Windows in a nice way. So the thing I always think, or the fundamental problem that is attached to that approach is that you have a trade-off here. You have a trade-off between the window size. You want to have a big window size to actually capture interesting information inside the window, but you want to have a small window size for memory and performance reasons. And then the second thing is, the question is now, when do you advance your windows? So if you just do your first window-based method, you might say, okay, this window goes to here, then I start the next window. And then you will find out if your window size was 2 weeks, to do one computation every 2 weeks might be not enough. So you're starting to overlap your windows and do the computation all over again. And since you wanted big windows, you're ending up reprocessing the whole data a lot of times, which is fine. I mean, usually the methods you apply to it might be not that resource intensive, but sometimes the feeling is you're really not using the computational resources in a good way. So to give you one example, when I was in Koblenz, I implemented a activity recognition method, also very much based on this approach. And if you actually looked at the feature vectors, they are now like a thing which just moves in space. The feature vector of 2 adjacent windows is almost the same. Just like continuously evolves around something, and then suddenly it goes to a different direction. So you're basically calculating all over again the same feature vector, very similar feature vectors. So here's a different approach, which we call this approach processing units. And the idea is also very simple. So instead of chopping the stream into windows, we are actually having a single function which ingests this or takes this incoming sample as an argument and does some computation on top of that. So the difference here is, first of all, I only ingest a single sample, and the other very important difference is that I allow the function to maintain state. So this is embedded into an object, and I have some state which is here in another variable. So this is, for example, Lua code, but you can, of course, do it in any language. And this function takes as a first argument the whole object, and it's allowed to mutate the state. So you're basically executing a state machine over the stream. The most popular method who does that, and let me just quickly go to it, is exponential smoothing. So if you're a little more mathematically inclined, I will just you'll find that pretty straightforward. Your update function, you have a single variable as state, single float value. Your update function, take that sample y, multiplies it by a number q, and then adds that to the state multiplied by a value 1 minus q. So I will not explain why this is something sensible to do, but this is really a concrete example of how this works in practice. And when I was seeing or learning about this for the first time, I was really like, wow, this is just so beautiful. This is really embracing the online method, and it's also doing something useful. So you see here a signal of latency which were measured, and I apply a exponential smoothing to it with a certain parameter. So you're seeing an exponential decay of the spike height. It will drop down, and if a new sample comes in, it will be pulled up again. So this is the basic dynamics which are realized by this method. So it's certainly something useful. And for example, if you have heard about Holt-Winters forecasting, Holt-Winters forecasting is just this very simple idea I just explained to you. And then you try to think how you would do trends and periods with this as well. And it's with the most naive thing you can think of, using the same paradigm and the same mathematical idea behind this exponential smoothing technique. This is Holt-Winters. And the programming paradigm is precisely the same. So when my first project at Circonus was implementing anomaly detection, and this is an example of how the method looks like. So here's a periodic signal, and then if it goes down somewhere, you will see an anomaly score ramping up, and then we mark the region for you where things are going out of the ordinary. And this anomaly detection method, I implemented it a few times, but in the end, I was really drawn to this design principle of doing online computation as a state machine. And it turned out to work quite well for us. So we didn't have any problems. In particular, the performance is really good because typically the update method is just a single sample. You're processing some float operations, and then you're done. So we liked that actually a lot. And we found that basic operations are readily implemented in as processing units. The second thing is, if you like your window-based method, you can still use it and put it in a processing unit wrapper. You basically have a ring buffer, which is just filled with new samples, and you can use that to do your feature computations all the way you like. So we're not losing anything. And the third very important thing is that they become composable. So if you're applying a window-based method, you have all the time the choices between window sizes, and you have to think about what are the windows I want to emit from a certain processing step. Or do I want to do a second windowing afterwards? So composing things involves a lot of choices and a lot of compatibilities which have to be enforced between the different components. Processing units, the rule is you get a single sample each time window, you produce a single sample for each time period. This is really, really easy to compose. So we observed this, and we thought, well, this is so great. And for many application scenarios, I was like, OK, I can just use 2 processing units, put them on top of each other, and here I have a new method. So we wanted to give our users the possibility to do that for themselves. So I give you a bunch of processing units, basic bits, and I allow you to compose them and build something more useful for you. And we built a query language around it. So this is actually released 2 days ago. It's actually now in the product, and you can use it. It allows you to build processing units out of primitive processing units. It has a pipe-inspired syntax that is should be alluding to people that like bash scripting. And the third property, you always need 3 bullets on a slide, is we have histogram support. And let me just briefly show you how it looks. So one application, for example, would be I have, again, this spiky metric we've seen before for the exponential smoothing. And I want to do anomaly detection for that. The problem is our anomaly detection method is focused around this whole winters and forecasting continuous data streams. So this doesn't really apply to this kind of metrics. It will just trigger an anomaly every time you see a single sample. But if you are doing a rolling mean of 12 hours across that to smooth it a little bit out, it will actually work. So here in blue, you see the rolling mean across the data. And note that we can do rolling means fine with the method. It's just like we could do an exponential smoothing, but for this particular example, the rolling mean was working better. And then we use that and then apply anomaly detection on top. And the query, how you would formulate it is just like I take the metric, and you want to have a metric kind here. You want to take a UID and a metric name. So this is a little bit lengthy, but you have to describe the source. Then you apply the mean value, and then you apply anomaly detection. So it's pretty natural. And the other thing is we have histogram support. So what we do here is we take the incoming stream, and then we rebucket the data. So we have a usual 1-minute sample data stream, and we now take 1-hour windows. And instead of taking averages, we take the whole histogram of all data which is viewed inside. And you cannot really see it well on the projector, but actually the whole data distribution is all the way up here. So for this particular amount of time, we have seen a sample distribution. This is a request latency measurements that goes all over the place here to 12K up. Usually, if you would look at this graph with the direct representation as a line, you would only see this line here lying down below. And this is a topic I've talked about a lot in statistics classes I've been giving for engineers. It's when you're viewing graphs, you're usually viewing mean values. You're seeing mean values of aggregated stuff. When you zoom out to an amount that you can no longer display the minutes. And it's important to know that and keep that in mind. So if you look at spike height, for example, you have to zoom all the way in to actually be able to see what the height of the spike was, because otherwise it will be just averaged out. It will be much lower. With histograms, you can get around that, because histograms don't take mean values if you aggregate. You just put more samples into the histogram. Right. Good. So now the last part, design of the Deker engine. So we have now set the scene. We have said we want to do online analytics. We have decided we use processing units. So how are we actually going to do it? And the problem at first sight seems actually not too bad. You have an input source, you have your processing unit, and you have the output source. Easy. We thought, OK, first thing, you just do it maybe a day or 2. However, if you're thinking more about it, you have actually a few challenges that are thrown at you. The first one is rollups. So we decided to have a really simple processing paradigm, but the samples that arrive on the queue actually come whenever the measurements were made. So they might come multiple times a minute. And the first step, I have to roll up the data into 1 minute aggregates, and this is a time where we really take a mean value here. So if you send us data multiple times, we either take a mean value and some other artifacts, but really summary statistics, or we store it as a histogram. But for this, let's assume we just do a mean value. So that's not so bad. However, if you think about over what the mean value should actually be taken, so the incoming samples have a timestamp, so you're not using the system clock. If you have different sources, they will have different timestamps. You can have late arrival, and you can have out-of-order arrival, with timestamps being not monotonic. And you can actually also have downtime. So if a broker doesn't send data and comes back up an hour later, for the processing unit, it is stateful. It still needs to see all the data that was transmitted by that broker. So we have to wait and really be able to let the broker catch up and push the data in later on. Another consequence I want to talk about here is you are not able to do real-time processing with Beaker, with our architecture. So it's not a high velocity or a high frequency engine we are building. This is because of this roll-up step. Because we are aggregating things by the minute, we cannot act in it before the minute is over. So we have a usual delay of around 30 seconds for that. We are not saying we cannot do any analytics within the minute. We still have threshold-based alerting, which is just under millisecond range of response times there. But everything that relies on processing units has a certain delay in it. Might not be a big problem because anomaly detection is usually also something that evolves over time a little bit, but that's for sure. Yeah. The second challenge is, I have not talked about it a lot, but it's actually possible for processing units to take multiple input metrics as a source. So for example, you might want to do sums across different or mean values across different metrics. So you have actually an end-to-end matching problem at the very first step in your pipeline. And this is not really trivial. We solve it by making the processing units know about the metrics here, but they are design decisions which you have to make at this point, and they are actually not entirely straightforward. And the third challenge is really doing the first two things I talked about at the same time. So this is where you really sit down and hate yourself for a little bit because the complexity is just pretty high to manage all that. It's all pretty much straightforward once you have sorted it out in your brain, but you really need to keep track of all the separate metrics, all the separate processing units you're pushing in, and a little bit also of performance, how you index your data structures and how you index your processing units and your metrics teams in order to make the matching halfway sane. But yeah. Now here comes so those challenges, they are just basically programming challenges. You have to sort that out. Here comes a challenge which is a bit more structural, and which is fault tolerance. So there are many confusing definitions of fault tolerance in people's heads, so I thought I might just put one on the slide, which I stole from a book by Berman, 2005, but I think it's still a good definition. So fault tolerance means that the service tolerates the failure of nodes without producing wrong output messages. Moreover, failed nodes must be able to recover from a crash and rejoin the cluster. And then you're not allowed to produce wrong messages, and you should eventually recover. There is no limit on the time it can take to recover. So it's just about you're not producing wrong results, and you eventually recover. And this is fault tolerance, at least to that book. There are different definitions out there. And actually, it turns out this is not so bad. Well, if you're using OmniOS, our favorite operating system, we have a service management facilities where it just restarts the program, the daemon, if it's going down. And you have fault tolerance. That's not bad. In Linux, you have systemd, you can do that. You have also watchdog processors, you can just do that. And if you are just ensuring that when you're going down or a problem occurs, you're failing and you're eventually recovering and you're able to publish valid messages eventually, then you adhere to the definition. However, for us, recovery can really take a long time. Anomaly detection, for example, takes a buffer of 3 or 4 weeks of data to be in order to have enough state to do a sane forecast, to see an anomaly detection. So we don't want to wait for this long. And actually, in order to be able to restart the nodes faster, not weeks, maybe 20 minutes might be acceptable or 10 minutes might be acceptable. We need to access the persistent metric store to replay faster. There is another design decision we could do is in persisting the processing unit state. The big problem here is updates. If you update your own method, you might have a different state, and then you need all the time to worry about state migrations, which can be a real pain. So we thought we'd just relearn the model and we ingest the data. So now the overall architecture has become a little bit more complicated. Second challenge is high availability. So by definition, a service is highly available if it continues to publish valid messages during a node failure. So this is the strong thing, high availability. There is a short reconfiguration period, which we think should be around 1 minute until the service has reconfigured or less than that. But this is really the thing we should be aiming for at this point because people are relying on this. This is a little bit more tricky. The thing we did for our other alerting engines is we just run multiple in parallel. And the authoritative one is always the one which was running the latest, so it has the most state in it. And then the oldest one is always able to output the messages. Now, if you have this high availability configuration, the nodes need to know about each other and have to ping each other and have health checks. And then if they discover that the master node has gone down, they need to make a failover and elect a new master. They have to agree on which one has the latest, the oldest things. So you need a little bit of complexity there. So the second challenge is scalability. So we want to be able to process as many processing units as we want. However, we don't need to scale infinitely in the amount of incoming metrics. So with 100 million metrics, we will be fine for the next years. So we don't take that off. And here's the next great design about the scalable beaker. It's just like, OK, you are doing multiple high availability clusters. You are having now a meta service which has to map the processing units to the clusters. You still have dependencies on the database at the back. And you're just pushing your data through. And internally, the high availability clusters have still the same configuration. They have this failover management. We thought, great, problem is solved. Just build it. Works. Superb. You might have noted the complexity of this whole thing just exploded. So it went from a little bit, you just sit between two queues, to a massive amount of complexity, which we were a little bit afraid of. So we went back again to the chair and thought a little bit. And this is the final design we came up with. So we are now splitting the service out into 3 different smaller services. First one is just a rollup service, which takes all messages it gets and then cares about the rollup. And then it publishes on a new queue all the rollup messages. Then there's a processing service, which is actually responsible for executing the processing units. And then there's a third service, which we call the duplication service, which takes in all messages it sees. So we allow explicitly to publish multiple messages all the time. And this thing in the back will make a best effort of deduplicating it. So speaking of messaging semantics, we in general allow for duplicate messages. So you cannot have exactly once delivery in this kind of scenarios. So you need either have at most once or at least once delivery. So we are shooting for duplicates. We allow for duplicates, so for at least once. But we will do a best effort deduplication in order not to overwhelm later services. And the deduplication service will also take care of which message comes from the oldest version of Beaker being running. And these 2 things are actually pretty, they are pretty simple services from a high availability and scalability perspective, because we are not wanting to scale about the limit of metrics we are going to able to ingest so much. This rollup service can run on a single node, and the deduplication service can also run on a single node. And the only thing that needs to scale is really this processing service. Turns out in that way, processing service can scale out quite easily. It maintains state. It has to restart again from the node. This is something we cannot take away, but you can get away with not having any failover scenarios, because the deduplication service later on takes care of that. You just have to ensure each processing unit is always executed of at least one worker. But you have no interdependencies. If one node goes down or something, you just have to bring it up again. So the complexity of this service is actually vastly simpler. Also note that we don't have communication between the worker nodes here. So if you know about the universal scalability law, law, the kappa term is 0, which is really good, right? So we have built that. Currently, we didn't spread it out across many nodes. We're doing thread level concurrency to test the scalability a bit. We're doing here around like 10 or 15 threads on a 6-core Xenon machine, so it's a pretty big machine. And we can do, for 100 processing units, we can process samples at 15 kilohertz for anomaly detection. And for 10,000 anomaly detection units, we can do 4.2 kilohertz. We need just below 1 hertz. So because we are only processing one sample a minute, so we live with very low throughput at this point. The only thing we are hitting is the memory consumption. So the memory will run full before we can actually exhaust the CPU. And actually, the processing units are so cheap to execute that the 90% of the CPU load we have here is from serializing and deserializing messages. So there is still a lot of performance tuning we can do about that. Right. So I will now conclude, just being like 7 minutes over time. I've talked about the implementation of processing units, and I've told you how we want to address the next challenges in monitoring. Quantile-based alerting, anomaly detection, outlier detection, all these things you can build with processing units. I've talked about K-qual and how you will be able to do your own processing units and compose them, if you like, within Circonus. I've talked about service orientation and how you can reduce complexity dramatically within your service by splitting it out into smaller bits. And I'm just happy to announce Beaker is coming out. We are having a late prototyping stage right now, and we hope to do it this year or early next year and be able to alert on these kinds of analytics things and have a fancier dashboard next year. Thank you very much.
All right, I would remind you if you guys have questions, raise your hand, and I'm going to run around. I know it's Friday. Come on, wake up. I think they still may be processing it at 1 a minute, your talk.
Maybe I can ask a question. Like, have you had experience with online processing systems? Have somebody built something like that? So what were your experiences with it? Or have you worked with such systems?
Yes, but in a very different sort of application. So it's and not at that, and also not quite at that scale, or at that scale, but in a much more distributed way, taking much smaller streams of data in many places and processing them at the leaf and then sending back really just monitoring and alerting data, or aggregated monitoring data and alerting data. So not nearly the same thing. Okay,
is it the computation at the edge level at the nodes? Yeah, that's also cool. So for example, this quantile-based alerting, we are currently also trying to push that on the nodes when we generate the histograms to have that computation right at the edge. Yeah. Hey.
Hey, great presentation, thank you. Histogram seems like a very obvious way to go. A lot of open source tools don't seem to be able to do it.
Yeah.
What is the challenge in them adopting that? What makes it so hard, given that it's such an obvious, better mousetrap?
Well, one problem that you will have using histograms is just the storage of them is much more complicated, because if you're doing the naive implementation, just like bins and counts and a list of them, you have no boundaries on the storage. And they're also a little bit tricky to get right. So what should be the bins? What should be the counts? There's, among the monitoring vendors, I think, a consensus around what that should be now. So basically limit the precision of your boundaries by like 2 or 3 digits. And this gives you basically you have it behaves like the precision of float numbers, the bins. So yeah, I mean, I think it's solvable. I think there's challenges around storing it in a reliable way, because the one thing you don't want your monitoring system to do is actually fail. So yeah, but I think it's also quite natural that the commercial companies will be a step ahead of that and might be in the near future. I mean, I haven't seen anyone, for example, InfluxDB or people who are doing like open source databases around monitoring really embracing this histogram paradigm. So I can't really speak for them. Yeah.
Anyone else? All right, let's thank Heinrich again.